Hello everyone, in this lecture we are going to talk about two different kinds of lone pairs. The first one is localized lone pair, and then the next one is the opposite, delocalized lone pair. From the name, what we see here is that the lone pair, which is two dots that usually we will draw on the item, shows that this pair of electrons belongs to this item that's in the molecule. And based on the name localized lone pair, that means this lone pair is on this item, it cannot move. So what does that even mean? That means this pair of electrons resides in the hybrid orbital. So it can be sp3, sp2, or even sp. It depends on the hybridization of that item. And because it is inside the hybrid orbital, it cannot move around. So it will basically assign to this item inside the molecule. For example, if we are looking at this molecule right here, this is the acetone. At this moment, we are still drawing the Lewis structure. So what we are seeing here is this oxygen have these two lone pairs on it. Based on your knowledge you have about the determination of the hybridization, we have two lone pairs and we have a double bond which include one sigma bond. That oxygen is a sp2 oxygen at this moment. So if we know this is sp2 oxygen, that means this oxygen, right, have three sp2 hybridized orbitals, and one of it will form the sigma bond with this carbon right here. I'm going to highlight with blue, and we know this carbon is also sp2. So the carbon will be right here and will form this sigma bond with that oxygen, and the other two sp2 hybridized orbital will drop right there. Now if we are looking at the carbon on the left or the carbon on the right, they are the same thing. Here, because it have two single bonds, four things around it, is a sp3 carbon. So for sp3 carbon, it will have four sp3 orbitals. So one it used up to form that sigma bond, to form that single bond with the sp2 carbon, the carbon in the middle, the blue carbon. And also it will have another three sp3 orbitals, and same to the carbon on the right side. So it will form that sigma bond, and then it will have this four sp3 orbitals in total. So what we are seeing here is we have those hydrogen, right? Hydrogen is 1s, so we'll put the hydrogen here to form the sigma bond, the single bond with the carbon, green carbon, or this black carbon on the right. So that is the sigma bond we are seeing here. So besides that, what we see is these two lone pairs, and these two lone pairs sit inside this sp2 hybridized orbital of oxygen. So sit there, it cannot move. And your question may have is here, where is this pair of electrons that is forming the pi bond? So that pair of electrons share between the carbon and oxygen through the pi bond. Pi bond is p orbital overlapping because both oxygen and carbon, they are sp2. So you have one unhybridized p orbital used up right here. So that is also the rule how to determine if these two lone pairs is localized lone pair. So because these two lone pair on the oxygen, which already have the p orbital used up by forming the pi bond between the carbon oxygen. So those two lone pairs is localized lone pair. In another word, it is in the sp2 hybrid orbital in this case. So what we are drawing here, it is a very important concept. This is so-called sigma structure. So in sigma structure, it basically shows you the backbone of this molecule. It shows you all the sigma bonds. The sigma bonds head-to-head overlapping of the orbitals. And also it shows you the localized lone pairs. So all these things cannot move around, okay? Especially like sigma bond, it move around, that pair of electron share move around, that means actually you are breaking that sigma bond. That is when reaction happened. So sigma structure shows the bond of the molecule and it cannot move around. So your question here is, what is delocalized lone pair? Delocalized lone pair. D means move around, right? So we are going to be able to move this lone pair around. So when the lone pair can move around, that means it's in so-called pi system. What is pi system? So when you have this is p orbital, okay? And if you have another p orbital, they are overlapping, right, from two atoms, and they are going to form a share one electron pair. They are going to form the pi bond. So imagine if you have more than two. So if you have one and two, the second one from another atom, and then the third one from another atom, they are all overlapping with each other, and they have some electrons sitting inside these p orbitals, then you will have a pi system. So pi system is overlapping p orbitals. So if you have lone pairs or the electrons inside the p orbitals in the pi system, it can actually move around through the whole system. It's not going to be just sitting between these two or between these two. It can sit between these two or share between these two. So that means the electron basically spread out through the pi system, through the p orbitals that are overlapping with each other. So that is a pi system. That is why the delocalized lone pair can move around, can be delocalized. So how to determine if that lone pair, that two dots you draw on the molecule, can be delocalized or it sits inside the sigma structure, sitting inside hybrid orbital and be localized? There are some rules behind this. So there are some rules. Rule 1, how to determine if this lone pair is delocalized. So if you see a lone pair, okay, and this lone pair is on atom and next to an atom, so next door neighbor, that atom has unhybridized p orbitals. In other words, if the next door is a sp2 or sp atom, then that lone pair on this atom you are looking at is a delocalized lone pair. So let me give you one example. If we have a molecule look like this, okay? So on one side, this carbon definitely is sp3, and then here, instead of have carbon, we'll have one nitrogen. We know that one nitrogen is neutral is 3 bond with 1 lone pair. Something look like this, okay? So now we already know these lone pairs, they are localized. And these lone pairs, we don't know, but it's on this nitrogen. So what we are going to explore is next door. The next door is this carbon right here. This carbon is sp2. Okay. So what does that mean? That means this carbon right here has a unhybridized p orbital, where that p orbital used to. it used to form one of these pi bond right here, right? So it have unhybridized p orbital. In this case, this lone pair right here, the highlight in blue, is delocalized lone pair. In other words, this lone pair actually can move around through the pi system. So where that pi system, let's draw this out, because we already know that this oxygen right here is sp2, right? You have sp2, the carbon is sp2, and in this case, the nitrogen is sp2 as well. Okay, so you have oxygen, you have this carbon, and connected to this nitrogen. All sp2, that means they all have this p orbital, okay, p orbital overlapping. So what you are seeing right here is you have this pi bond. So basically it tells you that, okay, at this moment, that's these two overlapping to share that pi, to form the pi bond. And at the same time, this lone pair, delocalized lone pair, sit in the p orbitals. But in reality, right, in this molecule, because you have this pi system, these 4 electrons will not just sit like this. Okay, they can move around to spread these 4 electrons. And that also gives you the idea of the resonance in future. So that is how we can determine the delocalized lone pair. That is the rule 1. Okay. And the rule 2. So if we can determine that lone pair is localized lone pair, then it cannot be delocalized, right? So if the lone pair is on an atom which already used p orbitals, then this lone pair is localized, because you don't have that p orbital for this lone pair to sit in, so those lone pair need to sit into the hybridized orbital. So example is right here, this oxygen have these 2 lone pairs. Because this oxygen already used up that p orbital to form the pi bond, so this 2 lone pair right here is localized. Because they are localized, so they cannot be delocalized as well. So either or situation. So the third rule here is, this is another situation that sometimes you will see 2 lone pairs on one atom. Okay, for example, here this is acetic acid. And we already know that this oxygen have 2 lone pairs right here. So theoretically, based on what we just talked about, this carbon, right? This carbon is sp2. So the lone pair on here, right here, is next to an atom that has a p orbital unhybridized. So theoretically, these lone pairs can be delocalized. So if there are 2, rule 3 is, if there are 2 lone pairs on one atom, only one can be delocalized. But this is under rule 1 first, right? So if we are looking at these 2 lone pairs here, because under rule 1, right, the oxygen, this lone pair is next to sp2 carbon, so this can be delocalized. And because there are 2, only one, I'm highlighting the top one, bottom one, you can highlight as well. So delocalized. So because this is delocalized, the other one has to be localized. That means it's sitting in the hybrid orbitals. So these are the rules that you can apply to determine if the lone pair is delocalized or localized lone pair. Why we care about this? So from now on, when we are determining the hybridization, we count the things around the atom. The delocalized lone pair do not count for hybridization. We're only looking for the number of localized lone pair and the number of the sigma bonds to determine the hybridization. Another area that we focus on the delocalized lone pair is that we can move it around. That give us the resonance. So we'll talk about resonance and hybridization in another video.